Listen up.
I know.
Were there any questions on 1 through 11? Anything that confused you?
No.
Okay, good. All right. We're going to talk about what kind of functions have inverses, what kind of functions don't have inverses. So here's one. I'm going to just write a really simple function. I'll tell you, this one does not have an inverse. Okay. Now we're going to, if you're thinking, well, wait a second, that's so disappointing. I thought he might have an inverse. We're going to modify him later so that he does have an inverse. But for now, let's see. Why does he not have an inverse? Well, let's say I plugged in 3. What comes out? 9. I plug in -3. I get, oh, wait a second. I get 9 again. Let's draw this line a little bit better. Okay, so these two actually map to the same value. So then the inverse would have to somehow take this as an input. And here's where the problem lies. This input would have to map back out to 2 different outputs. That's not a function. Now here's the thing. If you're like, well, could I mean, you know the shape, right? Could I draw that function and then talk about reflecting it over this line? If I took every single point and reflected it over that line, it would end up looking, I had a little bit of a hard time with that drawing, but that is possible. I mean, they actually call this a relation. It could be an inverse relation, but that is not a function because a function, like if you plug in 9, you can't pop out 3 and -3. Does that make sense? Does this ring a bell?
Yes.
Vertical line test?
Yes.
The vertical line test tells you, is this thing a function? So let's think about the original then. If our attempt at creating an inverse fails a vertical line test, what kind of line test is this guy failing? A horizontal line test he's failing, okay? So let me redraw the graph. So it's actually a very simple test. If you got a function, so this function, again, was the point, the x value 3 got us 9, and the x value -3 got us the same y value. So if you have a function where 2 different x values produce the same y value, then it fails a horizontal line test, and you could say that this thing does not have an inverse. Cool beans?
Mm-hmm.
So then you could draw a bunch of conclusions from that. You could say, well, let's say I start drawing a function, and I want this to have an inverse, okay? I'm going to say he starts increasing. Well, once I have him increasing, what can he never do now? Yeah, if he decreases, oh, I just failed the horizontal line test. So you got a function, you can kind of generalize this to be like, well, if your function is it has to either always be increasing or it have to always be decreasing. Okay, you can't double back. Does that make sense? Sure, there's no questions on that? Okay, so for 12, you're just, draw 3 graphs that would fail a horizontal line test, okay? And then for 13, you're going to draw 3 graphs that would pass a horizontal line test. 14 and 15 are very similar. They're just, this time you're being given a function. And let's do a little bit of review.
Those students are testing both at once. If you're only testing at one.
Exactly. You give that to Julia? Yeah.
So if it has an inverse, it fails the horizontal line test?
We'd say it passes. I mean, I guess you could, it's up to, typically the convention is to say that this passes a horizontal line test, meaning, can I draw a horizontal line that hits twice? No, there's no way to do it. So I'd say that this guy's going to pass the test, and he has an inverse. Whereas this guy, I can find a horizontal line that hits twice, so I'd say he fails. It does not. Okay, an inverse function at least. Okay, so a little bit of graph review. Okay, so does this function have an inverse?
Yes.
Well, let's look at the graph. Is it possible to draw a horizontal line that touches the graph twice? Nope. So he has an inverse. This is actually an interesting one. Does anyone know what the inverse of this function is?
The same thing.
It's the same thing, yeah, exactly. Because if you plugged in, like, if you plug in 5, you get 1/5. So the inverse function, you'd have to be able to plug in 1/5 and get 5. But wait a second, that's exactly what that function does, right? And you can also see how you could reflect it over that line, it would land on itself. Make sense?
Yeah.
1 over x squared. That marker's killing me here. All right, over data's head. Ooh. Go in. Boom. Money. What's that look like? Whoopty. Whoopty. He fails the horizontal line test. He does not have an inverse. How about this? Here's a question. Who this?
No.
Who this?
Guy
Oh, it's the same thing
left
moved up.
one.
Moved over, moved over. It's the same thing moved down.
It is. So Alyssa is touching on an important thing here. The domain is all reals. Is there any number that you could plug in that would make the bottom of this 0?
No.
No, you can't square a number and add 1 to it and get 0. That's not possible with real numbers. So that tells me that it's not like one of these guys shifted, even though I can see why you might think that this got shifted, but it's not quite that simple. Here's the thing though, when you go to graph this, say you did this, say you were like a little unsure and you're like, well, I'm gonna list out a couple points just to get my bearings. What does 0 get you?
0 gets to 1.
1. And then let's just plug in some arbitrary number like 2. What does 2 get you? 1/5. What does -2 get you? Oh, wait a second.
Oh,
That right there tells me that there's no inverse function because the inverse would have to map the number 1/5 backward to 2 and -2. That's not going to be possible. It does say use graphical, support your answer with a graph. So this tells me, what does this function do as x gets big?
It's small.
It approaches 0, and then this tells me that it's symmetrical across the y-axis. It's Mr. Humpty Bobumpty, okay? A great, great man. You guys got done so fast.
Well, Mr. Oliver doesn't respond.
I think we interrupted an important phone interview. He was like pacing around his room on the phone, like doing an interview for some sort of job. We're like, oopsies.
Kind of awkward.
How about that? Now this one's interesting because do you see on this one we were able to just by picking out 2 x values, we were able to see that there was no inverse. Do you guys see how we didn't necessarily need the graph to make that connection? Okay. This one's a little strange because if you plug in, it's the same thing. Plugging in 0 gets you what? 0, right? 0 divided by 1 is 0. How about plugging in 2? Get you 2/5. How about plugging in negative 2? Negative 2/5. So have we seen any problems yet? Is there any single y value that has to map back to 2 different x values? No. So you might think, oh, he's fine. He's got an inverse. But actually, if I graph him, what is he going to approach for large x values? What's the y value going to approach? 0. So this function has to hit 0, 0, like this. Has to go positive, but then come back and approach 0. The same thing on the left side, but for negative numbers. So does he have an inverse?
No.
Neat.
No.
Neat. Do we understand?
Yes.
Do we understand why the table of values was maybe didn't quite give us a good picture of whether or not this thing has an inverse, but the graph does a better job? Okay. Whereas this one, the chart alone probably would have sufficed to determine the non-invertibility. Okay. Moving on. I want to discuss 16 with you. So I am, in a minute or two, going to talk to you about, I'm going to show you a method that will get you the inverse. Any function that has an inverse, there's, well, I shouldn't say any function, but most functions you'll typically encounter, there's a method for calculating the inverse function. But on these ones, I want to keep it really simple on 16. What does, so 16a, what does this function do to its inputs? It adds 5 to them. So for example, this would contain the point, I don't know, 3, 8. So the inverse function, what's the inverse of adding 5 to something? Subtracting 5. Now, according to what we know about inverses, this function ought to contain the point 8, 3. Does it? If you plug in 8, do you get 3? Great. So that's the inverse function. Okay? How do we feel? Look at the next function. For b, what does that function do to numbers? Doubles them. What's the inverse of doubling?
1.
Cutting in half. Okay. Same story on 16b. Like f would contain the point, I don't know, like 5, 10, and the inverse would contain the point 10, 5. Cool beans?
Yes.
Good. Now, there is there's a weird one on here. C is not too weird. What's the inverse of dividing by 3? All right, D is the weird one. Why is that a weird one?
Because you can't just square root it. You can't just square it. Yes.
Yeah, so f of x is the square root of x. So let me think of a point that lives on here. Maybe, I don't know, 49 gets you 7. How about that? So the inverse would have to contain the point. When you plug in 7, you should get 49. Now, what kind of function does that? Or what's, maybe you thought of it as, what's the inverse of square rooting? Squaring. Are we okay so far? Now, there's just a problem here, which is we just spent a little while talking about how that function does not have an inverse. So it doesn't really make logical sense that he's the inverse of him, and he's not the inverse of him. The relationship should go both ways, right? So the key is to look at a picture. Because I don't think they know the answer of what are we going to do to fix it. Very good. Change the domain restriction. But, so here's how you can, this is a good way to reason this out, is you look at this guy and you say, well, his graph would look like this, right? And think about his domain and range. You guys remember this idea, how this guy's range is gonna be this guy's domain? So what's this guy's range?
0 to infinity.
0 to infinity. So this guy's domain has to be 0 to infinity. So drawing a picture, there's your reflection. So really, you're just getting half the parabola. So what you do is you add a domain restriction onto the function. All right? How do we feel about that? That's going to be probably the main thing that throws you off on this stuff, I guess. Is when and how do I put a domain restriction on my inverse function? Okay. So something to keep your brain ready for. How about E? What's the inverse of cube rooting? Cuban. Do we need a domain restriction?
No.
Because the cube root function is well behaved. The cube root function looks like this. So any horizontal line test issues? No. His inverse is just x cubed, no restriction required. How about F? You're going to need yeah. Yes, F is very similar to D. Your inverse is just fourth powering the number, then you got to put that domain restriction on there so that it works. All right, now this idea of just doing it like intuitively of like, oh, the inverse of adding 5 and subtracting 5, that works really good for very simple functions, but the more complicated they get, the more it's going to be like really challenging to do that. So I'm going to show you now. I'm going to show you kind of two ways to think about it. Did I tell you guys about the shoe thing?
What?
Socks and shoes?
No.
Okay, here's a function. All right, I guess I told you that class, I forgot. Okay. In the morning, you do a function. And it's, you put your socks on, then you put your shoes on, and then you tie your shoes, right? Call that tie. So what's the inverse of this? So this is a big idea here, okay? The first thing you do on the inverse is not to take your socks off, right? It's to do this, it's to undo this one first. So it's you invert each operation in reverse order. So you're going to untie your shoes. You're going to do shoes off, then you're going to go socks off. And by the way, I mean, just go, think of a domain range. What's his domain? Domain. Yeah, naked foot. What's the range? Shoe with tie, bunny ears. Okay. What's this guy's domain? Foot with shoe and tied bunny ears, and then the range is the naked foot. Okay. Cool. Make sense?
Where did he get the extra toe, though?
Toxic waste. Bootstraps. Yep. Okay. So for 17, the point I'm trying to make here is when you look at these, you can say so g of x equals 2/5 times x plus 4. So don't, you don't have to write this part down. Just listen to this part. What are the two? What happens to the input? What's the first thing that happens to the input if you plug an input in here?
Times by 2.
You multiply by 2/5, and then you add 4. So the inverse, better undo this first. It should subtract 4 and then divide by 2/5. And we know that dividing by 2/5 is the same as multiplying by 5/2, right? So this tells me that my inverse has to be subtract 4 and then multiply by 5/2. Okay, there's my answer. Now, most people have trouble with doing that mentally. Okay, not to say that you shouldn't try it. What's up?
Does it have to be, with the parentheses?
Yeah.
Okay.
Well, unless you want to write 5/2 x minus 10.
But
If you
it's
distribute
not
the
distributing in the previous function, or in the non-inverse function.
right, so this one you got like that's why the order is important. This is why I think the method I'm going to show you in a second is probably the most foolproof and like ironclad method because it's algebraic and you can't really mess it up. But if you look at what's happening here, if you multiply by a number and then add, that's how that looks. But if I want to subtract and then divide and then multiply the result, I have to use parentheses or else I've violated. If there was no parentheses, this would be saying multiply by 5/2 and then subtract 4, which is not the right order. So let me show you the algebraic method. Algebraic. It's very simple. Here's the idea. Hand banana?
Yeah.
Hand banana. What does an inverse function do? What happens when you invert a function and you have an xy point? What happens to the x and the y values? They swap. So the algebra to calculate an inverse function does exactly that. Ready? Okay, so G is y equals 2/5 x plus 4. So the inverse, I just swap the x and the y, okay? X equals 2/5 y plus 4. You swap the x and the y. Now that y represents the inverse function. So I have to isolate him now. What's the first thing I'm going to do if I want to isolate this guy? I'm going to subtract 4. Right? Subtract 4. Then what? Divide by 2/5, i.e. multiply by 5/2. So you see what I'm doing? And remember, the way I thought about this was, I mean, if you want to get kind of technical, what I'm doing is I'm basically inserting a function in here and asking what function can I insert here that would spit out x as the output. And that's exactly what this swapping does. So anyway, my answer then is, oh, look, it's the same exact answer. Cool beans? Okay. So when you do these in practice, I mean, I'm imagining, you might do this maybe mentally just to get a quick like sense of what's going on, but then this is probably what you're going to do to actually calculate the inverse. Does that make sense? All right, this question actually is asking a couple more questions. It's asking us to look at the x and y intercepts of both functions, and then it's asking us, what do we notice about the slopes? So let's do the intercepts first. So let's look at G. What are my intercepts? Someone give me one of them. Huh? Be more specific. We need 2 coordinates, right? Yeah, 0, 4. Okay, so that's the y-intercept. What about the x-intercept? X-intercept. I'll do the hard part. Lamau, this is a prank, bro.
4.
Oh, wait, let's. It's not a bad idea to throw out a number and see. Does that make sense? If I plug in 4 for x, would I get 0 for y? No. What do I have to plug in for x to make my y value 0?
You have to plug in -10.
-10. Very good. Suppose you're having trouble doing that mentally. You would just maybe go off in the margin, go 0 equals 2/5 x plus 4. When you solve that, you of course get Does that clear things up for you guys?
No.
That's the x-intercept. You guys are killing me. Not. It's a rough day for me, maybe. Okay, how about this guy's intercepts? Maybe I should draw the arrow down here, sorry. Because this is the function I ended up with. What's his, we can be clever here. What's his y-intercept gonna be?
-10, 0.
Close. If the original function has the point -10, 0, then this guy better have the point 0, -10, or else we made a huge mistake somewhere, right? They're inverse functions. So you have to have this swapping, right?
Mhm.
Can we confirm that plugging in 0 would get -10?
Yeah.
That checks our answer, right? It makes us be like, yeah, we got it right. That's correct. Okay.
Whoa.
How about this point? 4, 0. Can we confirm that does plugging in 4 get for x, get me 0 for y?
Yeah.
Doubly confident this is correct. Last thing. The slops are, looking for a different word here.
Opposite.
That's less close.
Reflect.
They're reciprocals. Good. Okay. This guy's slope was 2/5. What's this guy's slope? 5 halves. Okay, so if you have two, well, if there are two linear functions and they'll have reciprocal slopes, there's a more nuanced relationship if the functions are nonlinear, which you hopefully noticed when you did number 6. When you looked at the slopes, you had these reciprocal slopes, but they weren't at the same x values. They were actually it's at the point AB versus the point BA at corresponding points. They had reciprocal slopes. Okay. Do you want to do one more example?
Yeah.
Okay. I think 19 and 20 should be very straightforward. Let's do 21 as our last example, and then we got a little bit of work time here.
Get it? Do you get it?
What are you talking about?
Yeah, do you get it, Nikita?
Yeah.
You get it?
No, I don't get it. What?
The funny joke I just made.
I missed it now.
Highly intellectual humor.
Oh, yes.
Meme number. Lamau. Okay, so f of x is the square root of x minus 5. All right. This question is asking us to do a whole bunch of things. So the order in which you do them, I don't think really matters. And depending on, I don't know, for you, the order, maybe doing them in a certain order might make a little bit more sense than doing them in a different order. But anyway, let's get the inverse. Let's get the inverse using algebra alone. So F inverse, what do I do? What's the technique?
You
Instead of y, let's start simple. Instead of y equals square root of x minus 5, I'm going to swap them. So it's going to read x equals the square root of y minus 5. Do we understand going from here to here? You sure? If you don't understand, you're in trouble. It's just, I mean, nothing else is going to make much sense if you're stuck on this. We're okay? All right. I need to isolate this guy because this guy represents my inverse function, this y symbol. First step, square both sides. Then add the 5 over. By the way, do you see the order of operations? Subtract 5 square root is turning into square, then add 5. The order is being reversed. So my inverse function, first of all, is x squared Meaningful pause.
Domain restrict.
Yes, this. Wait a second, that doesn't quite work. That would be a whole parabola, and he wouldn't pass the horizontal line test. So the domain restriction would be right. X has to be greater than or equal to 0. Now to figure that one out, maybe you're thinking of it graphically, right? Maybe you looked at this one and said, well, 1, 2, 3, 4, 5. It looks like that. So his inverse has to look like 1, 2, 3, 4, 5, which tells me that the domain has to be 0 to infinity, right? So make sure you label your graph, by the way. This is F. This is F inverse. The other way you might have reasoned it out is, and the question is asking us to do this, what does F have? F's domain is, and his range is, what's his domain?
Domain is everything greater than 5.
Yep, so 5 to infinity. His range is
Everything greater than
0 to infinity. And how about the inverse? The domain is, what happens to these two sets?
This should be swapped.
Just another swap. The x's become the y's become the x's. Swappy, swappy. The range is 5 to infinity. Okay? Did we answer all the questions? We identified the domain and range of both functions. Check. We drew a rough sketch of both graphs to show the reflections of each other. Check. And we found f inverse of x. Check. So we got all three things. All right. Feelies intact? No?
Not one bit.
Taylor Swell's a boo-boo.
Feelings have been hurted.
Feelings cry.
No cry.
Feelings cry.
Crying